So I'm going to start with a walkthrough of how to actually download and install Discover. So the first thing you need to do to get Discover is to go to the Discover website. So you can go to kaleidoscope.com/discover. And this is going to have all the instructions you need to do the installation. The first thing you need to do is actually go to download here. Just put in your name and email, click submit, and that's going to download a zip file to your computer. Now, Discover runs basically in Python, so the only thing you really need to do before working with Discover is to download Python on your computer. If you're using Windows, which right now is the only thing that Discover supports, you're not going to have Python installed already with your computer. So you're going to need to install a version of Python to use Discover. If you already have Python 3 installed, then you should need to reinstall again. But if you haven't used Python before, or if you're using Python 2, you need to get a version of Python 3. So to get that, we just go to the Python website, python.org, and then go to Downloads and Windows, and then make sure to get the latest Python 3 release. So it should be Python 3.7. Right now it's at 0.4. Get the latest one, and then basically you're going to be able to download installer. Let me see here. Yeah. So you can also just go to downloads and go to download for Windows Python 3.7.4. So that's going to give you a basic installation file. You open that up, you hit run. And now, very importantly, in order for this to work with Discover, we need to make sure that this checkbox is checked. So add Python 3.7 to path. This will allow Discover to find the Python installation on our computer. If you don't have it checked, even though you have Python installed, Discover is not going to be able to find it, and things won't work out. There's a way to fix this later, but it's easier if you just do it during installation. And so once you have that checked, just click install now, and that's going to install Python on your system. I already have it installed, so I'm not going to do that right now. But once you follow through that installation, the way to check whether everything is working and Python installed correctly on your machine, and that Python path variable was activated, is to open a command prompt on your computer. So you can just go to the start menu and type in command prompt, and then type in Python. And if you have everything installed, then you should get a message with the Python version and these three kind of arrows, and here you can already start typing Python code. Now, we're not going to use Python this way in the course, but this is what Discover is actually built on. But as long as you have Python 3.7 something installed, then everything else should be pretty straightforward. Okay, so once you have that working, then go to where you installed Discover, or where you download the zip file, and go to, here I'm using 7-zip to extract the zip file into a folder. So just unpackage the zip file in a folder on your computer. And here are the files that are included with Discover. Okay, so here we have the plugin, so I'll show you how to install that into Grasshopper in a moment. We have samples here of Rhino Grasshopper files that already are integrated with the Discover components. So you should be able to open these up and start running optimizations right away. And you can look at these files for guidance on how to set up your own models with Discover. In source here, you have all the source code for Discover, which is where the genetic algorithm is implemented. So if you are a Python user, or you want to sort of mess around with some of the ways in which the optimization algorithm actually works, you can search through the source code. Static just has the files for the interface itself. So to launch the Discover program, we need to launch the server. So the Discover server is going to be running in the background and processing the whole optimization process. So to start that server, we just double click on this discover.bat file. That's going to launch a command prompt. And if it's your first time starting the server, it's going to take a few moments to download and install all the Python libraries that it depends on. So this should be done automatically. As long as you have Python installed, it's going to go through and download all these dependencies. And it's going to do so in a way that creates a virtual environment, so it's not going to interfere with anything else you have set up in Python if you're already using it. Once all of those dependencies are installed, it's going to start the server, and then it's going to open automatically a browser window where the Discover interface will be loaded. Okay, so if you have this, if you get to this point with the interface loaded in your browser, then everything should be working fine with the Discover server, and you should get this message that a connection to the server was established. Okay, so while you're using Discover, you're only going to interact with this web-based interface, but you have to make sure that this command prompt is running in the background, so don't close this window. Now when you're finished working with Discover, to shut down the server, all you have to do is close this window or hit Control-C twice. That's going to terminate the server and it's going to close that window. Okay, so now if you try to refresh this page, then nothing will load up. And if next time you want to start the server again, you just have to double click on that file. If you've already run it before, then all dependencies are installed. It's going to launch that server immediately and then open it up in your default browser. Okay, so that's the Discover server. The last thing we need to do is actually install the Grasshopper plugin for Grasshopper, so we can use those special components to connect our Grasshopper to the Discover server. So the only file you need for the Grasshopper library is contained in this Grasshopper plugin folder, and it's this .gha file. And all you need to do is then put this file into the components folder within Grasshopper. And that folder is hidden somewhere on your computer. It can be kind of a pain to find, so the easiest way to find it, I'll show you now. You just start up Rhino. So you start up Rhino, open up Grasshopper, and go to File, Special Folders, Components folder. And that's actually going to open up the folder on your computer where Grasshopper keeps all of its external libraries. So if you just started using Grasshopper, this folder is going to be empty. And for any library you want to install, you just put the file or folder that comes with the library into this folder. So to start working with Discover, we want to take this file and actually copy and paste it into that folder. Okay, and the next time you restart Grasshopper, you should have a new tab here. I have a lot of these, so you can't see the names. But you should get a new tab called Discover with the 7 Discover components loaded and ready to go. Okay, so let's start exploring some models and see how we can actually use these Discover components to connect to the Discover server and start running our optimizations. So I'm going to open up the test models for today's class. I'm going to start with a very simple model here called box. So I'm going to open up the Rhino file in Rhino. And then I'm going to open up the box start file. So it's a very simple model. It just has 3 parameters which control the length, width, and height of the box. So I have a point at the origin, I have another point controlled by these 3 parameters. We create a box, and then we just calculate the volume, and I'm outputting my volume here as my single metric. So it's kind of a dumb model, but it's a good one to test a very simple application of optimization. So if we have this model and we want to start running optimizations, here's how we set up the Discover components. We start with this basic component called Discover, and we just place that on the canvas. And this component will actually connect our model to the Discover server, so then Discover can run this model automatically during the optimization process. And the only thing we need to get this to work is to create a button and then connect that button to that component. And now every time we click that button, it's going to check to see if the server is running and then make a connection between this model and the server. So as I start working between Rhino, Grasshopper, and Discover, there's a lot of windows. If you have two screens, you can definitely use that to your advantage, but for my purposes here, I'm going to just dock these windows in my on my screen so that Discover's on the left side and I have Rhino and Grasshopper on the right. So now when I click this button, it's going to create a connection to that server, and then in Discover you're going to see that connection and then the file it's connected to. So in this way you can actually have multiple Rhino and Grasshopper files open and they won't conflict with Discover, because Discover is always going to have that connection to the last Grasshopper file in which you click that button and you made that connection. So you can also switch that connection between multiple files that you have open at any one time. Okay, so now that we have a connection to the server, we need to create our inputs that will drive the model. So we already have those inputs specified with these sliders, and all we need to do is just convert those to Discover inputs. And like we were saying before, there's actually 3 types of inputs that Discover supports, and they all have their own individual component. So we pick one of these depending on what kind of input we want. Now in this case, because I'm looking at the dimensions of a box, I have 3 continuous inputs. And in Discover, if the inputs are of the same type, like they have the same type and they have the same range, you can actually use these components to create multiple inputs at once. So you don't need to create a separate input component for each number that you want to generate. Here I want to generate 3 numbers, but they're all within the range of, I think, let's say we can make it from 1 to 10 units. So I can actually generate all 3 of those parameters at once. So this input, continuous input component takes 3 different inputs. The R stands for range, so that's the range of numbers that I want to produce. And that's specified as a domain type of object in Grasshopper. And I can specify that using the construct domain component here, where I can plug in the minimum and the maximum, and I get a domain out of it. But a quick shortcut that I often use is you can just type in that range or that domain directly within a panel. So if I do 2 backslashes, I could just type in 1 to 10, and Grasshopper will interpret that as a range for me. So now I've specified that I'm going to create continuous parameters that can range from 1 to 10. C stands for count, so that's how many parameters I want to produce. In this case, I want 3 of them. You can specify that with a slider or a panel, doesn't matter. And then this active just needs to be connected back to the Discover component. So this is what's going to trigger that component to execute and then ask the server for the proper inputs it needs to take for each iteration of the optimization process. And then once you've specified all the inputs, your parameter values are going to come out of the V output here. So here are my 3 numbers. And indeed they're within the range of 1 to 10. And now I just need to connect that to my point component. And you see here with our starting model, we had the 3 inputs broken up, and now we have them in the list. So a quick shortcut to take a list of numbers and to break them into individual outputs is to use the explode tree component. So explode tree will take a tree and then put each branch onto a separate output. And if we plug in our list, as we remember, when we have a list, we have a tree with just one branch. So if we want to put each of those output numbers, or we want to put each of those parameter numbers on a separate branch, we can just go here, right click on the input and go to graph. We can also simplify it if we want something cleaner. And then to match up the number of branches we have in our tree to the number of outputs here, we can right click on the component and say match outputs, and it'll basically create a separate output port for each of our parameters. And now we just swap those for our inputs. We can delete our sliders now. And here we have our model now connected to Discover. And anytime we change anything here, so for example, if we wanted to limit the range, it's going to output, it's going to update those, that parameter set and create a new set of parameters for you. And if you wanted to explore a variety of different options or to generate a bunch of random designs, you just have to click that connection a bunch of times, and each time it's going to connect to the server, and from the server get a set of new random designs. So this can be a quick way to also test the range of designs your model can produce. Okay, so once we have our inputs set up, we need to set up our outputs. So remember, to drive an optimization process, we need at least one objective. And here we have our volume being calculated. So for this simple test, I'm just going to set that up as an objective, and we're going to try to maximize that volume as much as possible during our optimization. So in Discover, we have two types of outputs. We have constraints here represented by the X, and objectives represented by the plus sign. So I'm going to create an objective, and as two inputs, here we specify the name. So this is pretty important to put this name here, make it something meaningful, because this will actually be represented in the Discover interface when we are visualizing and exploring the design space. So it's pretty important to name this in some way that you'll remember what that metric was representing. And then the value of that metric that you compute in your model goes into the V input here. Okay, so that sets up the objective for our optimization. And the last thing we need is if we want to capture a screenshot of each one of our design iterations, so we can later see like which design was what, we have to set up one of these screenshot components for Discover. So I'm going to click on that screenshot. It looks like a little picture. Place it on the canvas. It takes two inputs. The first one is the name of the viewport that we want to use to capture the screenshot. So here I can type in perspective to use my existing perspective view. So this input is pretty handy. If you input a name of a viewport that already exists in your Rhino model, it's going to use exactly that viewport. If you type in a name that there's no viewport that exists with that name, it's going to create a new floating viewport and give it that name, so then you can adjust it to the exact dimensions you want. Or if you leave this blank, it's going to actually use the viewport that you have currently active in your Rhino model. So it's a kind of handy little input that you can use in a lot of different ways. In my case, I'm going to type in perspective to ensure that even if I activate another view, when I run the optimization, it's going to definitely use this perspective viewport that I have set up. And you want to set up this viewport exactly the way that you want it to be captured. So if you have this kind of basic Rhino geometry or Grasshopper kind of visualization, that's what it's going to look like in your screenshots. So this is fine when you're testing a model, but when I do these things in production, I try to tailor that viewport as much as possible to give me the kind of visualization I want, because I might end up using these screenshots actually as final visualization files, and I want them to look good and be communicative. All right. So once you set up that viewport, then you connect the A's together once again so that the screenshot component gets triggered every time that the model gets updated by Discover. Okay, so there you have it. That's a very basic setup of Discover. That's the kind of minimal setup you need to drive this simple optimization. Again, we have 4 types of components in Discover. We have the main connection component. You always have one of these in your model. We have a screenshot component. You have at most one of these in your model if you want to capture a screenshot, or if you don't want to capture a screenshot, you leave it out. That's going to save some time and storage on your computer for sure if you don't have to store those files. And then finally specifying at least one output, which if you only have one, it has to be an objective. Okay, so once the model is set up, I'm just going to click on this button. You should click on the button to update your connection anytime you make any changes to the inputs or outputs, because once you click that button, it's going to connect to the server. It's also going to tell the server the exact composition of the model, so the server knows what kind of optimization to run. So make sure to click on that right before you start any optimization. And now we'll switch over to Discover, and you see the interface is very basic. On the left it has 2 buttons. The first tab is for Run, so this is where you specify the parameters of the genetic algorithm, and you actually run the optimization process. The second tab is the Explore tab, where you have some options for how you visualize the results of the optimization once you run an optimization and you start getting designs in this main part. So in the main part of the window, we're going to see our scatter plot once we start running the optimization. And on the right, we have another toolbar where we can see the designs that we've selected in the Discover interface, and we can also send those designs back into Rhino. Okay, so let's try to run a very simple optimization here. I have some default parameters for my optimization, and these are very basic parameters that you can use to just test the model to make sure it's working. So it's only going to generate 5 designs for each generation. It's going to go through 5 generations, and it has a 5% mutation rate by default, and 1 elite design, which means it's going to take the best design from each generation and automatically place it without crossover into the next generation. So this is a simple way to ensure that we never lose the best designs. Okay, so with those simple parameters, I'm going to hit Run. Now it's going to go through and generate my design options. So it's looking like here, as soon as optimization starts, we're going to see our designs popping into the interface as these bubbles. And so the bubbles in the interface are plotted relative to the 2 axes here. And by default, if you're just using one objective, it's going to put the objective value. So you can see here volume, this is what we named our objective, and minimize, this is the direction we want to optimize it for, on the y-axis, and it's going to put the generations on the x-axis. And this is a kind of default view for a single objective problem, because you can see the value of your objective, and also you can see how that evolves over time through your generations. So in the 0 column here, you see the 5 random designs created in the first generation, and then you see every design coming later. And because this is set to minimize right now, you can see that the designs get smaller in volume over time. Now in this view, we can hide this. We can use our mouse in the scatter plot view to zoom in and out on the scatter plot. We can also use our scroll wheel directly over any of the axes, and that'll actually zoom in just on one axis at a time. So that can be useful if you want to just expand one of the axes. Now as we hover over each dot, it's going to show us the number of the design and what that design looks like in the screenshot. We can click on any of the designs. It's going to put a black circle around it, and that will cause it to pop up in our designs interface. And let's just pick another design here. And if we click on any of these designs and we don't have an optimization running, it's actually going to send those input parameters back to Grasshopper. So once the optimization process is over, we can actually instantiate any one of these designs back into Grasshopper so we can further edit it. All right, if we switch over to our Explorer tab here, we have a variety of drop-downs which let us map other data from the optimization onto the dimensions of our scatter plot. So the scatter plot has 4 dimensions. It has the X and the Y dimensions here, and it can also represent data as the color or the size of each circle. So when we only have one objective, we only have really 3 pieces of data to represent. We're always going to have the design ID and the generation. So the design ID is actually just each design in order, and the generation basically combines the generations together. So when I'm dealing with a single objective, I really like to look at the x-axis as generations because it gives me the most sort of clear indication of how that optimization process proceeded over time relative to my metric. So ID and generation you're always going to have for any process, and because you always need one objective, you're always going to have at least one more thing here, but as you add objectives, you're going to have them all pop up here, so then you can change which objectives get mapped onto different dimensions if you're dealing with a multi-objective problem. Okay, so these are these 4 drop-downs. You have the same exact choices here, but for size and color, if you don't want to use that as a visualization dimension, you can just set that to none. It's going to just give you small circles with a gray color. So if you want something really simple, you know, and you have a single objective optimization, this can be pretty clear as a visualization. And then finally you have 2 checkboxes here, so let me just reset that. The checkboxes here allow you to either isolate the designs you currently have selected. So I've selected those 3 designs, and if I want to capture a screenshot of all the designs but just the key ones that I have here kind of highlighted, you can use that checkbox. Or optionally you can select just the optimal design. And for the single objective, we do have one best design in the set. If you have multiple objectives, you might have multiple best designs shown. Okay, and then the buttons below allow you to either clear the set of selected designs or reset the zoom so that you see all the designs again. Okay, so that's a basic overview of the Discover interface. So let's run a couple more tests here. So we saw here that we set the volume to minimize. If you want to change your objectives from minimization to maximization, you can do that through our context menu directly in the objective component. So on the objective component, we can right click and go to objective type and click maximize. And now we need to click this again to communicate our model structure to the Discover server. Now if we run this again with our small design setup, we're going to see that now the direction of optimization towards maximizing that component or maximizing that volume. So we're going to see the designs get bigger and bigger as the optimization process proceeds, and then we can also click here to isolate the optimal, so we'll see very clearly when any bigger design is found over time. Okay. So even for a simple example like this, we can see that we do get a sort of pattern or this kind of direction towards bigger and bigger designs, but we can see that still the biggest possible design hasn't been found, right? Because we know that the biggest volume comes from the biggest box, which has basically 10 on all dimensions. Because there's only been like 25 designs evaluated, it hasn't actually been able to locate the best one. So if we wanted to get better designs, we have to basically increase the scale of the optimization problem or the optimization process, and we can do that with these 2 values. We can do that by sort of increasing both the number of designs that we're evaluating per generation as well as the number of generations that we're producing. And both of these values will increase the number of designs that the optimization algorithm produces, which will increase the time that the optimization takes, but it increases it in 2 different ways. And the intuition here is the more designs that the algorithm produces in each generation means the more diversity of designs and options it's able to evaluate. Because remember that the optimization process happens iteratively over generations, and each time it only looks at the designs in the previous generation. So the more designs you have in each generation, you can think of it as the more knowledge that the algorithm is able to store, or the more kind of diversity or variation it's able to explore during optimization. And that can be important depending on the complexity of your model. The more complex the model is, the more likely that there's so much variation that just having a few designs will not allow the algorithm to actually explore the design space sufficiently. On the other hand, the number of generations controls the number of steps that the algorithm actually takes to evolve your designs. Because the evolution process only happens at each generation, you really need a sufficient number of generations to actually do follow this evolutionary process. Even if you have a ton of designs being evaluated at each generation, if you don't have enough generations, it might never be able to actually follow those patterns it's discovering towards the best designs. So you always have to play off these two numbers, and there's never like a right solution for how many designs per generation or how many generations you should have. This is something that you'll find experimentally, but there are a few good rules of thumb for getting started. For example, you'll see that Discover always defaults with this 5x5. It's a very simple setup. It's not enough to do any kind of optimization in a real problem, but it's enough to go through the process very quickly just to make sure your model is working. And so starting from that, you can increase these numbers gradually as you test the model, and usually I like to increase the numbers together. So I'll go to a 10 by 10, or I'll do like a 25 by 25, or a 50 by 50, all the way up to like 100 by 100. And it sort of makes sense for the two numbers to scale together because they're both sort of different ways to do further exploration of the model. But in general, the most critical one, I think, is the designs per generation, because that's going to be baked into your model for the whole optimization process. In terms of the number of generations, you just want to make sure that you have enough generations that you're not stopping too early, and you're not stopping before the optimization process has been able to kind of run to its fullest and find the best designs. So for a number of generations, you can actually set that to be anything you want, to be a really high number, and then you can just monitor the optimization process in real time. And if you see that no better designs are being produced, you can actually stop that process early. So now if we run an optimization with these higher numbers, we can also increase the number of elites if we want to store more of the best designs in each generation. And if we run that again, we'll see that the number of designs increases. We might have a more higher probability of getting better designs actually starting from the very first generation, which remember is random. So if we get a good design here, it's just based on pure luck. But as we keep going, we're going to see that we become more and more likely to get better designs. And it's not just that we're getting better designs in each generation, it's that all of the designs in each generation are trending together towards better and better designs. So you can see this kind of movement of these columns higher and higher. And that's because not only is it discovering better designs, but as it's discovering better designs, those better designs become more likely to become parents for creating new designs. So you see the entire population moving towards higher performance. And that's really what you're looking for with a genetic algorithm. Because the thing works through generations, it's never quite enough to just think about what the best design is. You're really looking for this kind of trend where the algorithm is pushing the entire design space towards better performing solutions, right? So by the last generation, you can see here, we've done a really good job to sort of maximize the size of that box. And by the end, almost all the designs will be clustered in that area. Okay, so let's look at our next model. So the next model I want to look at is the hill example. So I'm going to open that up in Rhino. And then I'm going to open up the Grasshopper model in Grasshopper. So this is another really simple model. It has two continuous inputs, and the inputs are just controlling the x and y position of a point in the x and y plane. That point is then projected onto the surface that we have in Rhino, and then I'm just extracting the z coordinate, the height of that projected point, as our metric. And the goal of this optimization problem will be to find the coordinates of the point which has relates to the highest point on the hill. So it's literally like a hill climbing problem where we're going to try to find just experimentally through the optimization process where the highest peak is. And the way I've set up this problem is you see that there's these two lower peaks. And this is a typical test case for seeing if an optimization algorithm can avoid that problem I mentioned earlier of focusing or converging too early on a local optimal solution. So if we have a more direct optimization approach that just follows the kind of local conditions of its design space, it might follow this all the way up this hill and then get stuck there because it doesn't see anything better locally. So a good optimization algorithm will be able to actually avoid those local areas and find the best possible solution, and the genetic algorithm is actually very good at doing just that. Okay, so let's go ahead and connect this model to Discover. I'm going to go through the same process again, but do it a little bit kind of quicker without describing each step, just so you can get a feel for it. In this case, I have a couple more continuous inputs, so these ones, I have a choice. I can define them with just one input component, or I always have a choice to just create a separate input component for each one of these inputs. It's up to me. I just have to specify how many values are in each component set. So here, just to do something different, I'm going to define two separate input components, continuous inputs. The range here I'll take from my slider, so it looks like it's going from 0 to 10. So I'm going to type in 0 to 10, or if I have a range that starts at 0, I can actually, as a really quick shortcut, just type in the higher bound, and it's going to assume that the minimum is 0 because this is set up as a range input. Right, and then I'm going to copy and paste that below as well. So this gives me my two input values, and I'm just going to swap those into the model and delete my sliders. So I have my input set up ready to go. I could just click that connection to generate random results. Now I need to set up my objective. So I'm going to drag out one of these objective components. The name I'm going to set to height. And I'm going to plug in my value here. And finally, if I want to capture a screenshot, I'm going to create a screenshot component connected to Discover, and then this time I'll show you what happens if I don't specify anything. It should just take the currently active viewport, so I'm going to make sure that perspective here is selected and active in Rhino. Alright, so I'll press that button one more time to make sure everything is connected. You can see here I'm connected to my hill model, and now I'll hit run. And again, by default, these objectives are set to minimum, and I actually want to maximize that value. So I'm just going to hit stop to stop the optimization process. I can do this at any time, and it's just going to stop where it's at and let me go back to Grasshopper. And I'm just going to right click on the objective and type in maximize, reconnect to the server, and hit run again. So you can see the design's getting better and better over time. Each time we find a new design, we see it kind of highlighted here because we've set optimal to be isolated. And you can see how over time it gets closer and closer to this point, and already by the second generation, it's really close to the peak. And from here on out, it might fine tune that a little bit and find kind of slightly better and better solutions. Okay, again, at any point we can stop this process. And we can use this interface to explore the different design options. We can select some, and then we can actually reinstate that back into our model. All right, so let's look at one more example before we break. Actually, we're going to look at two more examples. Let's take a look at this pill example. So this pill, it's another really simple test model, but it's going to allow us to start looking at cases where we want to actually use more than one objective. I'm going to load this model in. Here we can see what it looks like. So this model has 3 inputs, and the inputs are controlling the radius of 3 circles, which are then lofted to create this kind of curving form. All right? So these are 3 radii. They're used to control the radius of these circles. So I'm basically moving a set of control points on a set of curves, and then I'm revolving those curves into this sort of extruded lofted surface, capping it, and then at the end I'm calculating the area and volume of that shape. So I have the surface area of the shape and the volume of that shape. Okay, so let's now set up this model for optimization, and the problem we're gonna solve is we're gonna try to find the shapes, the design of the shapes which have the smallest surface area with the biggest volume. So this is a volume to surface area ratio optimization problem. It's also a very common problem in product design engineering, because typically the surface area of something, let's say like a barrel we use for storing wine, the surface area somehow relates to the cost of an object, right? Because it changes the amount of material we need and the space we need to store it, while the volume is how much stuff we can store. So it's very common to have these problems of designing something that has a minimum surface area, so it has a minimum kind of shape, but can store the largest amount of material. Okay, so we have 2 objectives here, so we actually need to start setting up this model with two objective outputs. Okay, everything else is the same, so we're going to create one discover component. I'll make this button again so we can connect to the server. And now we again have 3 continuous inputs here for our sliders. This time I'm going to cluster them together and just use one continuous input component to create all 3 of my parameters, and these are varying from 0 to 5. So I'll just type in 5 here. Okay, so I have my range set, and I'll connect that input to discover. And then I'll use my explode tree. Oops. I'll use my explode tree trick, and I'm going to graft and simplify that list of outputs, and then go to match outputs to get all of my parameters on different output streams here, and then swap those in for the parameters like always. Now I have my model connected to discover, so I can test different input parameters. And now I'm going to go over to the right here and set up my objectives. So again, I'm going to have 2 objectives. One for the surface area, so I'm going to plug the surface area in here and call this surface area. And that objective I want to minimize, so I want that to be as small as possible. And then I'm going to make another objective here for my volume. I'm going to call that volume. And this one I want to actually maximize, so I'm going to switch this in the context menu of the component to maximize. And then just so I can see what all the designs look like, I'm going to create a screenshot component. And again, I'm just going to keep my perspective screenshot active so I don't have to specify a name here. Alright, so let's click the button to reconnect this to Discover. And I'm going to run this optimization. Let's just keep it with 10, 10, and then 2 elites. Let's click Run. It's going to start creating designs. And what you'll notice right away, if we still have Isolate Optimal selected, we no longer have just one optimal design visible. We actually have a range of these optimal designs. We still have these transparent designs which are not optimal, but now we have a set of optimal designs instead of just a single one. And this is a common characteristic of design or optimization problems that have more than one objective, right? Because when we have one objective, it's very obvious what the best design is. It's the design where that value is as low as possible if it's something that needs to be minimized, or as high as possible if it's something that needs to be maximized. Now, if we have situations of multiple objectives, meaning we have 2 or more, it's not obvious what the best design always is, because there could be situations where those 2 objectives trade off with each other. So in this case, we have some situations where we have very small designs with very small surface areas, so they're performing well according to the surface area metric, but they also have very small volumes. On the other hand, we have large designs which have very big volumes, so it performs very well in that metric, but it also has large surface areas. So you can't actually decide which of those are better. They're both better at their own objectives, or you could say they kind of trade off between those objective values in different ways. And so the optimization algorithm actually considers those designs equally optimal, right? Because they're handling that trade-off in different ways. And once we finish this optimization process, we can see that in fact we form this kind of set of optimal designs that are all lined up in this row. And we can see all the way down here from, if we look at our surface area objective and our volume objective, they're both minimized. So these are these are optimal designs that optimize for the surface area objective at the expense of the volume. And if we scrub through, we see the design gets bigger. And these are designs that optimize the volume criteria at the expense of the surface criteria, and everything in between, right? Every different design in between. Now at the same time, we see other designs over here which are not optimal, and that's because they're not optimizing that trade-off as well as other designs. For example, with this design, we see that for its surface area, we have a design that actually is better both in surface area, has a smaller surface area, and is better in volume. So we say that this design, number 109, actually dominates this design number 0. Because it's better in both objectives, we can confidently say that this design is optimal and this one is not, because there's another design that's better than it in all criteria, in all objectives. On the other hand, we can't really say the same thing about these 2 designs, right? Because while this one has a smaller surface area, this one has a bigger volume. So we say that these 2 designs are equally optimal. Okay, so we find that with problems of more than one objective, which is quite common in the design problems we're going to solve, we actually have this condition of there not being a single best design. And all that means is we must then decide which of these designs is appropriate for us, right? The algorithm will reveal the set of best possible designs, but we have to decide how we want to navigate that trade-off and select the final design solutions. But the algorithm nevertheless is very good at pushing this set of designs as far as it can, and what you'll see is it'll always form this kind of barrier as the algorithm is pushing into the space and finding the best trade-offs to these two objectives. And the way you can think about this is you can look at your objectives and you can imagine this kind of imaginary point, which we call the utopia point, which would, in an ideal world, optimize both of the objectives at once. So for example, we can imagine a design which maybe has 0 surface area, right? So infinitely small surface area with a huge volume, and that would be somewhere over here, right? Now, in the physical reality of this design space, that's not possible, but what the algorithm is doing is trying to push these designs closer and closer to that utopia point. So if you look at a more complex multi-objective model, you actually see this sort of barrier or this front of good designs sort of getting closer and closer to that utopia point. Okay, so that is our simple multi-objective example, and just to show how this works, let's just change this example from one that has 2 objectives to a problem that has 1 objective and 1 constraint. Remember, we need at least 1 objective to run this process, and we can specify any number of constraints we want. So let's just say in this case we're going to look for the biggest volume, so we're going to keep this volume objective for maximization, but we're going to change our surface area metric to, instead of being an objective that wants to be as small as possible, we're just going to set that to be a constraint which just needs to meet a certain condition. And we'll see here from our previous example that an average surface area is somehow around 250. So I'm going to make this constraint, and I'm going to call it surface area. And now for the constraint, I need to specify both the type of constraints. So if I right click, I can go to constraint type. And my constraint will say that the surface area must be at least or no more than 250. So the way we define that as a constraint, we say that it must be, this is the criteria that must be met, it must be less than, and then for the t component here, the t input, that's the target, we specify the target of our constraint, right? So if we want to set up the surface area metric as a constraint that cannot be more than 250, we say that the constraint has to be less than 250, right? So when we specify these, it's the thing that needs to happen. It's the thing that judges or characterizes a valid design. And now we'll plug that surface area into our constraint. I'll click the button to reload the connection to make sure that Discover now knows that we want to treat this as a constraint. And then I'll run the process again. And now what you'll see is we're back to a single objective problem, right? So our scatter plot shows the generation, and it shows the volume here as our single objective. But what we see is another kind of visualization here where we have these hollowed out circles. And the hollowed out circles represent designs that broke one or more of the constraints. So these are not valid designs. It basically means that the value of their surface area was bigger than 250, bigger than our constraint setup. Now, because of the nature of these constraints, the constraints won't show up when you're selecting axes, right? Because these are things that just need to be met. We most often don't want to actually get into the exact values of those constraints. We just want to make sure that they're met. So it's a kind of Boolean. The thing we really want to look at is the value of our objective. All right, so constraint you can think of as just another condition that controls the model, even if it doesn't express itself as an objective. And this can be useful because you saw with a problem with 2 or more objectives, there's not really a clear answer for what the best solution is, right? So if you want if you want the optimization process to always give you one best solution, another approach, but let's say you have a bunch of metrics you want to consider, one approach is to just pick one of those metrics as the objective and then set all the other ones as constraints with some benchmarks, and then you're always going to get a single best design outcome that both meets the constraints and also optimizes your objectives. So for example, this design here is the optimal design we found, which has a surface area no greater than 250, but has the largest volume. Okay, so it's a very simple kind of demonstration of why we might, given a model with more than one metric, how we can set that up as either a multi-objective optimization problem, which might yield more than one optimal result, or a problem of one objective and a constraint, which will yield one best design subject to those constraints.